All right, so now we're going to do day 5. So day 4 was we converted some points from rectangular to polar and back and forth. Part B of that, we did some graphing, entire equations. Now we're just going to look at some special kinds of graphs that occur. My goal is to expose you to this. It's not meant to, you can memorize these, no point. I mean, the rows is not that hard to memorize, but some of these other ones, even just the names of them, is hard to say, to pronounce, and even spell, because this is supposed to be Lemni. So when I typed that in, I had it backwards, but lemniscate. So this is a lemniscate. This is a limason. That's an S sound, limason, and Archimedes and the rows. So just trying to expose you to this is my goal. You will not see these again. You would not see them in Calc 1, but you would see them in Calc 2. You would see some polar graphs in that. So I just want you to have seen them, have experience with them, and that way when you need to learn what you need to learn for that, it's not such a shock. So first off, just what these look like. Again, don't have to memorize these, but anything that is a cosine and then a multiple of theta, or r equals some number out front sine and then a multiple of theta, will produce a rose shape. Now it might have different petals, could have any number of petals, depending on what n is, if n is odd or if n is even. But typically it does have some symmetry to it. There's always some symmetry when you're talking about roses. Limasons is r equals, and it's going to be some number plus or minus cosine theta or sine theta. We'll produce something like that. And there's all kinds of different names on there, and I apologize. One of the homework questions asks you for what type is it. I will never ask you that on a test or a quiz. There's a few, like a dimple one. There's there's a bunch of different kinds. I don't expect you to know that. I'd say just guess on that. Don't worry about it. If it ends up messing up your score, I can go back and just give you credit for it. So that's not a big deal. Don't worry about it too much. Don't worry about what kind of a limason it is. Lemniscate, these are squareds. So a squared, and we got cosine 2 theta or sine 2 theta. Obviously, change in sine, cosine, and stuff like that will change which coordinate it is, how it's oriented, but it's going to make like a figure 8 kind of shape like that. And then Archimedes spiral is probably the coolest one. And also, this is the only one that just goes uncontrollably. Keeps going out, spirals out, has no bound, just never really stops spiraling. But this is r equals theta. Kind of a cool one to graph. So, like I said, just want to expose you to these as we're doing this. You don't have to memorize any of these, how they match up or pair up to anything. So, first thing I want to do here, this is a special type of limason, is a cartoid. It's going to have a new shape too, but it's basically it's one of these special kinds. So first of all, let's just graph it and look at it. We could do this first. I could plug these in. So if I plugged in 0, what is cosine of 0? Remember, cosine of 0 starts at 1, so that'd be 1. 1 times 2 is 2, plus 2 would be 4. Cosine of pi over 2 was 0, so 0 times 2 is 0, 0 plus 2 is 2. Pi, cosine of pi is -1, double that, it's -2, plus 2 is 0. 3 pi over 2 would be 0, so 2 times 0 plus 2 would be 2. And at 2 pi, you're back at 1, so 1 times 2 plus 2 would be 4. Now that could help if you plot those points. So when theta is 0, I have a radius of 4, so 1, 2, 3, 4. When I'm at pi over 2, which is up here, I have a radius of 2. When I'm at pi, it's 0, so if I'm facing that way, I don't go out any. If I'm down at 3 pi over 2, I have a radius of 2, so 1, 2. And then when it's 2 pi, that's wrapping all the way back around. I'm out here again. So it doesn't really, that kind of helps a little bit. It doesn't really tell me the whole picture. So that is a little helpful, but let's look at the whole thing though now. So again, we're going to put this in, make sure you're in polar, make sure your mode is in polar down here. So I'm at polar and radian mode. And let's see, so we'll go y equals, so 2 plus 2 cosine theta. And I graph it. And there's what's really happening with it. So it should look like that. And I've got my points down pretty good. It comes out a little bit this way. Kind of a sideways heart looking thing. I guess it looks better on the calculator than here. But what kind of symmetry does this graph have? So if you look at this, and this is actually, we don't necessarily want to say the x-axis, but if you say the x-axis, it means the same thing. But that's like the polar axis. So it is about the polar axis. I'll say about the polar or x-axis. And whoops. So why do you think that is? Well, you think about, for me, I think the strongest connection here is cosine has to do with your x. It's how you find your x. So it's going to be, it's going to reflect about that. There's other reasons why too, but that's kind of the main one. Is you're hovering. I think a cosine function goes back and forth. It hovers up and down about that, and cosine tells you the x coordinate, so that it's got to bounce back and forth from the x's. With sine, it's actually going to be another way. If I change the sign, it's going to kind of look like a heart going down. So it'll be like a double like that, or it'd be this way too. So it's going to be reflected about the y-axis. Now, if you happen to change this, and your calculator change it to a minus instead of a plus, I'm supposed to do that in black, but I did red. If I change it to a minus, let's go down here, and I'll actually put them together. So 2 minus 2 cosine theta. There's the other way, so that would reflect it across the y-axis, so it flips it the other way. Okay, so I'm not going to try to draw that in there in the same thing. It just basically flipped it this way over. Okay. Now let's do some analyzing, some testing. How to test and tell symmetry and stuff like that. So I mean, you can look at the graph, but what if you don't have a graph and you want to tell is it symmetrical or not? So this first one, and what it is if you replace r and theta with r and negative theta and it produces the exact same thing, then it's symmetrical about the x-axis. If you replace with negative and negative and it produces the exact same equation, then it's about the y-axis. If you just do a negative r and a positive theta, then it's about the origin, which, remember, the origin is, if you look at this guy as an example about the origin. Okay, so if I were to rotate it all the way around, 180 degrees, it would be the same picture. So that is about the origin. That's actually about the x-axis and the y-axis too. It's all of them. It reflects every which way. So how to check though without the graph? Because like this one, I don't have a graph of this. And I don't want to do the graph. I just want to know, is it symmetrical? And checking symmetry can actually help you graph it too. Because you could do, like if I knew that this was symmetrical, if I did the test and I knew it was symmetrical about the x-axis, y-axis, and the origin, I could actually just do the first quadrant and then repeat it everywhere. So that would save a lot of time if I was trying to graph this by hand. So use the appropriate test to prove that it's about the y-axis. So I want to check about the y-axis, which means I'm going to try that. And you could try this too. This is going to be simpler. So I'm going to take the r out. So it's r equals 4 sine 3 theta. Take out the r and replace it with negative r. And take out the theta and replace it with a negative theta. Okay. And now I want to simplify it. I want to see if I get the exact same. If I end up with this when I'm done simplifying, then it is symmetrical about the y-axis. So first off, if I had 3 times negative theta, that would just be negative 3 theta. And if you remember with sine, this is back in Unit 5, when you have a negative angle in here, the negative pops out front. Okay, if you have cosine, the negative doesn't matter. And what that is remember, sine is your y-axis. Sine has to do with your y-axis. So in the unit circle, if I open up theta this way, here's x, here's y. If I change it to negative theta, it means I'm opening the other direction. So now I have a negative y. If I open up this way, negative theta, if I put a negative theta in there, can't really see the negative anymore. But if you open up negative, your y changes, but your x doesn't. So that means your sine changes, but your cosine doesn't. So if this was cosine negative 3 theta, you could just get rid of the negative. It disappears because it's the same thing. But with sine, it pops out front. So it actually pops out like this, which ends up popping out front because it'd be 4 times negative sine. So it'd be negative 4 sine 3 theta, negative r. If they're both negative, that means they're positive. So that gives you the original. So check, it is symmetrical about the y-axis. Okay, so if I were to graph this, it would be symmetrical about the y-axis. Okay, and this guy here, we want to analyze this. So and Math Excel is going to ask you to graph it and then analyze it. So it might be easier to put into Math Excel. I'm sorry, to put in your calculator. So I'm going to type this in my calculator, and it's kind of fun to watch how it graphs, because it's not like it graphs like this and just rotates around slowly. It actually kind of goes like that, kind of how you draw a star. So let's look at this guy. So the domain on this guy, domain, remember, has to do with the thetas. So is there a theta that you cannot plug in? And on this one, just think any theta I can multiply by 4, and I can take the sine of any theta times 4 too. I can, sine of any radian measure. Remember, if it goes up, it's just like wrapping around. So if I did more than 2 pi, it's just going to come back around. I can do less than 2 pi, I can do less than 0. So anything works. So for the domain of this, you can pick anything you want. And then for the range, it's like the r's. So what's the maximum r that comes out on this? Well, we can analytically do it, or we can look at the graph here. And looking at the graph takes a little longer, but the largest r basically means how far away you are from the origin. So the largest r is probably on one of the tips of these petals. Okay, so if I did some tracing here, just started moving, get towards the end of the petal there, about how far away am I? Again, it's not really, it's like 2.76 is what it's saying. That's not exactly perfect though. It might help to do it analytically then. So analytically, I got to look at what's the largest value this could possibly be. 3 sine 4 theta, the largest it could possibly be. So, yeah, and this is actually going to help me answer this question too, the maximum absolute value of r. So think sine of theta. If you remember, that the highest that ever got was 1. And the lowest it ever got was negative 1. Okay? Now, me putting a 4 in there doesn't change anything, because I'm still doing sine of angles. So if I had 2 pi in here, or maybe I should say pi over 2. So pi over 2, give me a maximum value of 1. Well, if I take pi over 2 times 4, that's 2 pi. That's now sine of that would be 0. So that didn't make it bigger or smaller. So this goes from negative 1 to 1. But when I multiply by 3, something now we're between, and maybe I write it this way. So sine theta is between negative 1 and 1. Putting a 4 in there does not change that. If you want to try it, graph it. Graph it still bounces back and forth. It's just going to bounce faster back and forth. But the moment I put a 3 in there, now it's a negative 3 to 3. And that is your range. And those are included. So it can be negative 3 and it can be 3. Now, is this continuous? Just looking at the graph, does it have any holes or gaps or jumps or skips? It does not have any holes in it, so yes, it is continuous. Does it have symmetry? It has symmetry about the x-axis. We could check it if we wanted to. I can visually see that. The y-axis, and about the origin. Boundness. So is it bounded? So basically, does it go up forever, down forever? No, it doesn't. It only has limits on how high it can go and how low it can go, so it is bounded. So yes, it is bounded. Basically, the only one that's not bounded is this guy here. This guy just goes crazy. Just keeps going higher, lower, left and right. Just goes spinning out of control. The rest of these are bounded. They're, they just, as you graph it, it'll just keep doing this. 4 pi, 5 pi, 6 pi, 7 pi, 8 pi. Just keep doing circles. So it is bounded. Then the maximum absolute value of r, well, if r goes between -3 and 3, the absolute value of that is 3. So the maximum r value, whether it's positive or negative, is 3. Okay, so that's kind of how you analyze those guys. So don't worry about memorizing these. I need to memorize the shapes. I need to memorize which equations give me which shape. Just know how to analyze them mostly. Know what's going on with the r's and the thetas and that. So hopefully this helps, and please let me know if you have any questions.